This session introduces extraction and demonstrates how extraction is modeled in Aspen Plus. So extraction here it refers to liquid-liquid extraction or solvent extraction, and it's a technique used to separate liquid, as the name implies, liquid mixture, right? Or mix the two components or compounds, both in a liquid phase, right? That forms a homogeneous mixture. And the way it works is a third phase, right, which is a solvent. An organic solvent is contacted with the mixture, and one of the components dissolves in that organic solvent. And when that mass transfer occurs, or when the solvent extracts one of the components in there, it forms an immiscible phase, right, with the other material, right, allowing separation of the two phases, new phases form. So extraction can be single stage process or a multi-stage process. There are various configurations, can be co-current, counter-current, cross-flow fashion, right? So it's not, it can be modeled. There's a lot of flexibility to the modeling in aspect. We are going to see two forms of these as we move ahead. We'll attempt to solve the problem. An ethyl acetate stream is found to contain 70% acetate, with the remainder being acetone. So that's our feed, our mixture, the miscible phase. For ethyl acetate to be useful in a downstream process, concentration has to be decreased. So we want to decrease the concentration of the acetone to 5% or less. So we are going to do this by contacting the mixture with water. And the water should extract the acetone, right, and form an immiscible phase. So there should be an acetone solution, right, which should form an immiscible phase with the ethyl acetate stream. Yeah, so we have our components, our property method. Move to the simulation environment. So we're going to use a decanter to model the extraction. It's the first alternative or solution. So we'll mix the two streams, two feed streams, the solvent phase and the liquid, and decant. To move this. Okay. Now that the flow sheet is complete, we specify the stream parameters. It should be water, says 1 kilogram of water. So the same basis. That should be. We go to our decanter and we choose the key component for the liquid phase, the second liquid phase, to be water. It's the extract phase. And we run our simulation. the stream results. Show max flows. We've been able to remove some of our acetone. Uh, now 0.1 kilograms left in the lean stream. So we can compare that to the ethyl acetate stream, which is the feed. We can see the fraction of acetone dropping. So if we head back to the problem, it asks us to determine the remaining concentration from the first part. So the other two questions are repetitions of the first one. So we're just going to complete the flow sheet. Right, I'll be take the contacted fresh water, same as flow rate, take it to that should be it for the second run. Then we can do same for a third run. And in each case, we contact the lean stream with 1 kilogram water, same conditions. So we should be able to run the simulation now to have our results. So here we are just going to compare the lean streams in the feed. Acetate, one lane 2, and then lane 3. So we're going to see that the flow rate and concentration of the acetone drops. It keeps dropping. Somehow about that, and we have about 2%. It takes about 3 stages to complete or to achieve the desired specification, right? So this is one way of solving or achieving or simulating extraction, right, in Aspen. And but we can see it's very cumbersome. And if we see, we used a total of 3 kilograms per hour of water. In each case, we used 1 kilogram. So we see that it uses a lot of water. And if we were to look at our extract streams, this is the total amount of waste generated from the process. So there are other ways of achieving the same thing. More resource that are more resource efficient and better overall. And one of those is a countercurrent extraction. So if you and the idea there is it's a single unit, right? So the entire extraction occurs in a single unit column, uh, and over here, if this should be our feed material, you see that it is contacted with partially spent or already spent, partly spent solvent. Right? And at the exit of the unit, it's the already stripped, already uh, lean material or feed material that has already encountered some solvent meets pure solvent. Right? And overall, this improves the efficiency of the process in terms of resources and meeting the product specification. Fortunately, there is a unit dedicated for this in Aspen. So we are going to head back and do that. So maybe you should create a new simulation so we can compare or save and edit this, save this as another file and edit. Just going to edit that, delete all of these. Come here. So the unit for extraction. Okay, that's fine. Connect all the required streams. Right. Same problem. Could have maintained the feed streams. Wouldn't have to do this. Same. Same things. And when it comes to the column specification, it's a number of stages. We're going to start with 3 stages. We want to maintain the same temperature throughout the operation. So we specify the stage temperatures. That should be it. And the key component. So we select the material in the feed phase that should be in the raffinate that we expect to recover in the raffinate. And here, the solvent phase that should be in the extract. And we go specify the pressure. That should do it. Should be able to run the simulation. Now that we have results, we can go and see the so maybe I should rename these streams. This should be the raffinate. Where we expect the ethyl acetate. This should be the extract. Where most of the water goes. We can come back to our results. And then we see that most of the acetone flows with the water now. And we have the ethyl acetate being recovered in the raffinate stream with 88% purity. And we could compare this to what we achieved from the first process. In this stream. 93% purity and similar flow rate of the product, the desired product. So increase the number of stages. Let's make it 6 with water on the last stage, the bottom. So there are some instructions for allocating the stream. The rich stream, the feed stream should be on the first stage, and the extract should be on the last stage. Temperature profile is modified, and so is the pressure. You should be able to run this now. And go for the results now. So the flow rate stays around the same point, achieving similar purity as in the first case, 93%. Similar to what we got with the much complicated process. Right. So even using 1/3 of our material, right, with just 3 stages, we're already attaining 88% purity. And just by increasing the number of stages, we're able to hit our target while significantly cutting down the resources used and the wastes produced. Alternatively, we could drop the flow rate, we could increase the flow rate of the water. Say use half of what we were using in the first place. So increase the flow rate to 1.5 kilograms. And then use the 3-stage process. So drop the number of stages. And then we should be able to run this as well and look at the results. So in similar fashion, we are just by using half of what we used in the first process, we are achieving similar purity, right, with 3 stages. So overall, this process is much more favored and better. That brings us to the end of extraction in Aspen Plus. Thank you.